Okay, welcome to EGR445 598 Mechanical Engineering Systems. And in today's class, I'm going to talk about, or I will work out some problems on design of springs. So here is the tentative plan for today. So first, we will look at design of springs. In last class, I gave you some concepts on how we design the helical springs. In today's class, I would actually work out the problem on helical spring design, and I would also give you the design methods for leaf spring. So in today's class, we will look at helical springs and leaf spring. So that would be the first part. Then I'm going to talk about the concept of power screws. In the last class, I kind of talked about turnbuckle. Turnbuckle is again a screw assembly. What do we mean by screw? Screw means basically you have a nut and a bolt. So the bolt or the screw has external threads, nut has internal threads, and these two types of threads match one another. And what happens is, depending upon whether the threads are cut clockwise or counterclockwise, you can control the direction of motion. In the case of turnbuckle, we have clockwise threads on one side, counterclockwise threads on the other side. So when we rotate the nut in one direction, say clockwise, then both the screws or both the bolts either come together or go apart. It totally depends upon in what orientation the threads are cut. In the case of turnbuckle, application is load transmission, not power. So turnbuckle is supporting the load, not power. Power is force multiplied by velocity. So in the case of turnbuckle, velocity is 0. Turnbuckle is used for static load transfer. On the other hand, power screw is used for transmission of power. Concept is one and the same. You have a nut, you have a screw, you rotate the nut or you rotate the screw and induce the motion in the other component. But in the case of turnbuckle, what you do is it's stationary, it's static. In the case of power screw, the motion is continuously updated or it's dynamic. So that's why it is called as power screw. Another concept that you will notice where the design principles are same is something called as the C-clamp, wherein what you have is you have a nut which is attached to the housing, you have the bolt, and then you turn the bolt to attach two components or to attach some type of load, or that will be used to maybe glue two pieces of plywood or to apply some load. Design principles are similar, but again, the C-clamp is used for clamping or static application. It's not a power transmission device. On the other hand, power screws that are used in lathe, milling machine, some drilling machines, CNCs, 3D printers, routers, their purpose is conversion of rotary motion from the motor to the translational motion of the slide or the tool. In the case of maybe lathe, the rotary motion is converted into the translatory motion of the tool that actually turns the part. In the case of milling machine, what happens is the tool is rotating, but the slide is translating, and the translational motion of the slide again comes from the rotary motion of the motor. The other important advantage of power screws is mechanical advantage. So where does the mechanical advantage come in the picture? Mechanical advantage is nothing but amplification of force or torques by variation of speed. I want you to think about this concept for a minute. You have this motor. This motor has some power capacity. So it has some torque, it has some speed. Power is torque times speed. You equate that power to the power that is transmitted to the tool or to slide. And in that case, it's a translational motion. So you're going to have force times the velocity. Now, I want you to evaluate these two equations. If I decrease the translational velocity of slide, I would get enormous increase in the force. What that means is I can have a very teeny tiny motor running at extremely high speed. I can use a power screw to convert that small torque, high speed into small velocity and high force. So that way you get enormous mechanical advantage, and that is used in a lot of applications. And we will talk about it once we discuss the power screws. Now, there are two types of screw jacks that typically we see. One is the usual screw jack that you see in practice for lifting weights. And there is a toggle screw jack, which is used in typically when that screw jack needs to be compact. For example, if you have had experience in changing your tire, the screw jack that is provided in the vehicle, slightly older vehicle, is sort of a toggle jack that you run. There is a central screw clockwise, counterclockwise, and as you rotate the screw, the jack goes up or jack goes down. So which is classic turnbuckle. Think about it, turnbuckle turned into a power screw. We will talk about it when we talk about screw jacks and power screws. So next topic that I'm going to discuss today is power screws. And the topic after that is I'm going to start introduction to gears. Introduction to gears. Gears are used for power transmission. We will talk about the law of gearing. We will talk about the design principles for the gears, and we will also talk about different types of gears and then what we can achieve with a typical power transmission such as gear. Okay, with that, I'm going to start with what we discussed in last class. First and foremost, for a helical spring design, does anyone remember the important equations that we discussed in last class? So first and foremost, we have this C. This C is nothing but the diameter of the coil divided by the diameter of the wire. Then the shear stress equation tau is 8 times PD divided by pi d cube 1 plus 1 divided by 2c. And this equation comes from mechanics of material where we perform 2D analysis. Now, you can actually use something called as K, which is the Walsh factor. This is used for 3D analysis, where the curvature effects are taken into account. The next equation is K, which is the stiffness. Is P divided by delta, is force divided by deflection. And the last equation is equation for delta, is 64 r cubed n p divided by gd raised to 4. And energy stored in spring, I'll just write this down. It's 1/2 K times delta square. Now with this, we are ready to solve problem. Just let me give you an equation for the Walsh factor. So Walsh factor is 4c minus 1, 4c minus 4 plus 0.615 divided by c. And the idea is we are going to use these equations sequentially, step by step, and then that would give us the spring design. So I'm going to start with a problem. Design a spring that elongates 120 millimeter when load is equal to 300 newtons. Determine the wire diameter, coil diameter, number of turns, spring index is a design parameter, which is the ratio of capital D by small d, is given as 6. Shear strength is 420 Newton per millimeter square. Shear modulus is 84,000 Newton per millimeter square. So this equation, first and foremost, we have to use the equations that are needed to find the coil diameter, the wire diameter. So we'll start with the first equation. Design stress And in this case, they don't say how to solve this. They don't tell us whether we have to look at the Wahl's factor or we don't have to look at the Wahl's factor. What we can do is we can just assume a 2D mechanics of material concept, and then we can find out 8 T. Now D is the ratio, D by D is 6. I can say 6 times D by D cube 1 plus 1 divided by 2 times 6. And from here, you should be able to find out the value of D. So quickly use your calculators and tell me what is the value of D. So we can, the answer that I get is 3.4 millimeters, which is, I would approximate that to 4 millimeters. So this is ignoring effect of curvature. Right now, just for this very first problem, I want to take into account the effect of curvature. So if I were to do effect of curvature, it would be 8 PD pi d cube multiplied by K, which is Wahl's factor. So I would write this KW. KW is Wahl's factor. KW is given as 4C minus 1, 4C minus 4 plus 0.615 divided by C. So 4 times 6 minus 1, 4 times 6 minus 4 plus 0.615 divided by 6. And can you please quickly calculate this? And I got this answer as 1.25. Then I'm going to substitute 8, 300, 6 times D pi D cube 1.25. And tell me, if you consider the curvature effects are also called as the three-dimensional effects, what is the value of diameter you get? And my answer is 3.7 millimeter. So I'm going to approximate this to again 4 millimeter. Yeah. The next part is we need to find out number of turns. So delta is equal to 64 R cube N divided by GD raised to 4. Now, one thing I want you to understand is they have given us the elongation. How much is that elongation? 120 millimeters. They have also given us the load, which is 300 millimeters, 300 newtons. So 120, 64, 300. R is diameter divided by 2. So 6 multiplied by 4 divided by 2 is 12. So 12 cube times N divided by 84,000 multiplied by D, which is 4. And from here you should get value of N. And my answer is 78 tons. Now, next thing is, let's look at how does the spring look like. So what we have, we have a spring like this. From here, this is how the spring is gonna look. This is the wire diameter. This is the coil diameter. So our wire diameter is 4 millimeter. Our coil diameter is 24 millimeter. What we need to do is, we need to find the length of the spring. So length of the spring is, if you think about it, there is this imaginary wire, imaginary wire, imaginary wire, imaginary wire. And that is because it is turning in a circular shape around the z-axis. So that's why the total length is going to be N multiplied by small d plus N minus 1 multiplied by C plus delta external. So 78 times 4 plus, this is clearance, by the way. C, I should write that down, CL. N minus 1 is 77 multiplied by some clearance. Say I'm gonna say 1 millimeter plus delta extension is This is also assumed to be 20. And you can add this up, and that will give you the total number of, how much is it? 409. 409. So 410 millimeters. Any question, concerns? Yeah.
How did we get delta exit?
Oh, I assumed.
Oh, okay.
So this is assumed. Clearance also assumed. Any questions, concerns? Online students, any questions? Is this space okay, or am I going too fast, or everyone understands the material? If you don't, please stop me and ask, okay? Because we are covering a lot of material in a very short period of time. Unfortunately, that is how the summer class goes. Okay, the next part is I want to talk about design of leaf springs. And if you look at the textbook, there are two techniques that are given to design a leaf spring. And I will explain both the techniques. So, design of leaf spring. So, leaf springs are designed on the basis of bending. So, what is the simplest leaf spring? So, if you think about it, this is the beam, and this beam is supported on either side, and then you apply a load onto this beam. What happens is this beam kind of bends. This beam bends. You remove the load, the beam goes back to its original shape. So here there is something springiness. As long as the vertical deflection of the beam is within the elastic region, after removal of the load, the beam will go back to its original shape. So this is a very simple example of a leaf spring. Now, in the case of leaf springs, how do you find out the stiffness of the leaf spring? And that, if you look at the mechanics of material equations, if you have a load which is simply supported, P, and if you have this deflection, and I'm going to call this deflection delta, I'm going to call this deflection delta, then the stiffness of the leaf spring is P divided by delta. So what is the load applied and what is the corresponding deflection? But usually a single leaf spring is not used in practice. You will have multiple leaves so that the spring is stronger. And usually there will be some full length leaves. So if you think about it, there is going to be something like some full length leaves And there are going to be some partial or half length leaves. And that actually will make it stronger. So what happens is you have the main leaf, then you have additional leaves, and now you need something to keep these leaves together. So what you have is you have a central plate. And this central plate usually is held in place by bolts. So there will be one bolt here, and there will be one bolt here. There will be one more bolt over here. And one more bolt over here. And that is how a leaf spring would look like. So if I were to draw this as a sketch, the leaf spring would look something like this. And clearly, there will be eyes on either side. Those will be attached to the chassis. And then there will be support that will be mounted or attached to the axle. So in other words, the vehicle, and I'm not showing the tire, but tire could be somewhere here. So the wheel could be somewhere here. So that is how the leaf spring will be attached. Now you will have something called as the full length leaf. You can have graduated length leaf. And then you are going to have something called as the U-bolt. And then usually you would have some type of bushings over here. So I'm going to give you both the procedures. So procedure 1. Determine strength of each leaf. And since the leaf spring is designed from bending principles, the equation is M divided by I is equal to F upon Y. So what you do is you find out M per leaf, which is F divided by Y multiplied by I. And for each leaf, B of T ratio, it comes from the design data. Material, usually you would use spring steel, also comes from the design data. And Y is T divided by 2. So if you look at all the terms on the right hand side of this equation are known. So we can find out the value of bending moment per each leaf. Then for the leaf spring design, total M, which is M total, is a design parameter. M total, the amount of bending moment that the whole leaf springs needs to support will be given to us. So total bending moment is given to us. I value, it's a rectangular cross section, is going to be BT cube by 12. So next step is we can find out number of leaves. This is N. N is total bending moment divided by bending moment per leaf. And this again comes, the denominator of this equation comes from step 1, and the numerator of this equation comes from the design equation or the design constraints or the strength or the design requirements. Next step, step 3, is you have to find out the radius of curvature. Now for radius of curvature, remember the equation m divided by I, f divided by y, e divided by r. And this is the classic equation of bending. I'll just give you a rough idea what that means. When the beam bends, two things happen. First of all, you'd get stresses across the beam cross section because the top fibers are compressed and the bottom fibers are stretched. So you're going to have compression on top and tension at the bottom. The other thing that's going to happen is this beam is going to curve, and this radius of curvature is given by R. So whenever you are trying to design, there are two components to design, and I want you to think about this equation a little bit carefully. Let's understand which quantity is helping us to design the cross section. The cross section of the component is decided by I. This is actually the geometry. So geometry is decided by this equation m divided by I. You have two choices to find out I. So what you can do is you can equate m divided by I is equal to f divided by y and determine I. The alternate approach is you can use m divided by I is equal to E divided by R and determine I. Now some of you may ask me, what about the third combination? Third combination is F divided by Y is equal to E divided by R. This equation does not include the geometry parameter I. So this equation cannot be used for design. On the other hand, you have top two equations, m divided by y, m divided by I is equal to f divided by y, and m divided by I is equal to E divided by R. Those two equations can be used to determine cross section. The first equation, when you use, it is called as the strength-based design. Why is it called as the strength-based? Because please understand F is nothing but the strength of the material, the maximum amount of stress that the material can withstand. That's why this is the strength-based design. And when you use the second equation, which is called as the deflection-based design. Now, some of you may ask me which approach to follow. And the idea is you follow any approach, but you need to make sure that your design is safe from the strength point of view and your design is safe from the deflection point of view. Because you don't want to get into a situation where the design does not fail, but the component deflects so much that it's no longer to perform the intended function. Imagine you have a car and you sit in the car and the whole car deflects. Car can run, but car has deflected. You won't feel safe driving such a car. So what you want to make sure is you want to make sure that the design is safe from the strength point of view as well as the deflection point of view. And that is what is needed to find the radius of curvature. So for radius of curvature is using the equation m divided by I is equal to f divided by y is equal to e divided by r. You can find r is equal to e times I divided by m. And there are guidelines for radius of curvature in the design data book. So there are guidelines on permitted R for the leaf springs. And the last step is we had to find out deflection at the center. At center. And that is delta is equal to L square divided by 8R. And you can find out, so this actually defines the entire leaf spring design. Any questions on the leaf spring design? There is an alternate procedure that actually I will give you that talks about the list, the considering the full length leaves and half a length leaf. So procedure 2. So in procedure 2, the step 1 is determine B by T ratio. And this comes from the design data book. So when you open up the design data book or machinery's handbook for leaf spring design, they will give you the recommended B by T ratios for different applications. So if you want to design a leaf spring for locomotive application, there will be certain B by T ratios. If you want to design a leaf spring for automotive applications, there will be design ratios or guidelines. Second step is determine effective length. And this effective length is decided based on the geometry. For an example, many a times the center between the wheels or axle distance is given to you in the case of cars, in the case of locomotive. So what you have to do is you have to look at where the axle is and then try to see what is the maximum possible length you can accommodate to mount the leaf springs. So this actually comes from geometry. Third step is equate maximum bending stress of full length leaf to safe bending stress. And FB is equal to 18 times M divided by BT square 2 times HG plus 3 times so NG. NG are number of graduated leaves and number of full leaves. And bending moment M is given by the equation W times L divided by 4. And that comes from the equation where we assume the load is simply supported and L is the effective length of the leaf. And once we have this, you can find out the value of B, you can find out the value of T, and at this time, your leaf spring is completely designed. Okay, so what I'm going to do is I will just solve one problem on the leaf spring design. And I don't think I have asked you to work out any problem in the homework or the quiz. But it's good to know how this design process can be applied to leaf spring design. Again, you can follow procedure 1 or you can follow procedure 2. And at the end, your answers are going to be similar if you started with the same type of materials. So I'll work out a problem. A carriage spring or a locomotive spring, I'll say just leaf spring, is 1000 millimeter long and it's built with 75 millimeter wide and 10 millimeter thick leaf. The central load is 7500 Newton. Bending stress should not exceed 105 Newton per millimeter square. Determine radius of curvature and number of leaves. So in this particular problem, sigma B is 115 Newton per millimeter square. E is equal to 200 Newton. E is the Young's modulus, so 200 kilonewtons or 10 to the power 3 Newton per millimeter square. And I'm going to use this equation, sigma B is equal to M divided by I multiplied by Y. Sigma B is 115. M divided by I is 75 multiplied by 10 cube divided by 12 multiplied by 5. That gives M is equal to 143,750 Newton millimeter for each leaf. And if you look at the way this leaf is, something like this. So total bending moment is equal to W times L divided by 4 is equal to 7,500, because that is the central load, multiplied by 1,000 because this is the length of the leaf, divided by 4 is 1.9 10 to the power 6 Newton millimeter. So number of leaves is equal to total ending moment per leaf, which is 1.9 10 to the power 6 divided by 143,750. And the radius of curvature R is equal to E times I divided by M, which is 200 10 to the power 3 75 10 cube by 12 divided by 143,750, which is 8 millimeter. Oh, 8 meters, sorry. So that is how a leaf spring would be designed. Okay. Any questions? Any questions from online students? So next topic. Okay. No, next topic we are going to talk is design of power screws. It's a little early, but what I will do is I will give you all a break of 15 minutes. So next topic that we want to discuss is the design of power screws. So what are power screws? Again, as the word suggests, those are screws that transmit power. So we have a bolt or a thread, and then there's a nut. And this screw could be attached to a motor. So this could be attached to a motor. And what happens is, as this screw turns, either in the clockwise or counterclockwise direction, this nut can advance or can retract. So in other words, the rotary motion of the screw is converted to translational motion of nut. Now, unlike turnbuckle, you expect this motion to be continuous. For an example, a classic application is a 3D printer. In the case of 3D printer, you have a stepper motor. That stepper motor, by means of a coupling, is attached to a lead screw, and there is a nut on the lead screw that goes up and down or forward and backward depending upon the rotation of the motor. Now, one thing that I want you to remember is there could be mechanical advantage in this power transmission system. What that means is, if you think about the power of the motor is given as T multiplied by omega, where T is the torque and omega is the angular speed. Or angular velocity. If you look at the P of the nut, is force multiplied by the velocity. So this is force multiplied by translational velocity. By the conservation of energy, energy can neither be destroyed nor be generated. It can only change form. So in an ideal case where there is no friction, I can write this equation as P motor is equal to P nut. P motor is T times omega, is equal to F times V. Now, typically, electrical motors, they are designed to run at very, very high speed. So the omega value for the motor is quite high, anywhere between 10,000 RPM to 12,000 RPM. Torque value is typically low. The translational velocity of the nut is typically lower compared to the angular velocity of the motor. What that means is you get significant high force amplification. So because of the way the system is, you are gonna get a complex or basically high force amplification. Now, this power screw design is based on the principles of friction. So what does that mean? If you think about an inclined plane and a block of mass m on the inclined plane, this angle is called as alpha. If you look at the power screw, I'm going to show you the design of power screw. It will have a screw which is nothing but a helix and this angle is called as the helix angle, which is same as the angle shown on the left. So alpha is equal to helix angle. Now, the other important aspect is the friction between the block and the slide. So mu is the coefficient of friction. And there is a concept which is called as the friction angle phi, which is tan inverse of mu. Now, I want to show you a very practical example, and that kind of demonstrates what do we mean by friction angle. I want you to visualize that we have this flat surface, and on this flat surface, we have this mass. So what would be a good, so for example, this mass. I have this mass on this flat surface. Right now, there is some weight of this mass, but there is also a normal force, and mu times the normal force, there is a frictional force. So if I start making this plane inclined, 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 clearly there is a component of weight that's going to push this mass down. But the friction force is opposing its motion. But there comes an angle at which this mass starts sliding down. And that angle is nothing but the friction angle. The friction angle is the angle at which the mass starts sliding down because of its self weight. And if you want to write this equation, we can write this equation something like this. So this is m times g, which is the weight, and this m times g will have two components. One component will be in the direction perpendicular to the motion, which is mg cosine theta or cosine alpha, and the other one would be mg sine alpha And then there is going to be the coefficient of friction mu that will resist the motion. It's going to be mu times the normal reaction, which is mg cosine alpha. And if I equate the forces in the horizontal direction, so forces in the x direction, summation of forces in the x direction is equal to 0. I get an equation mg sine alpha is equal to mu times mg cosine alpha, and this alpha limiting is nothing but tan inverse of mu. So what it means, if the helix angle is less than friction angle, so if helix angle alpha is less than the friction angle, the screw is called self-locking. And if helix angle is greater than friction angle, then it's actually called running screw. And I will explain it to you in just a minute what it means. So have you seen some screws and nuts where in order to hold the assembly in place, you have to apply the force? If you reduce or if you remove the force on its own, that nut would drop down. In certain cases, you would notice that even if you let the force go, the nut will be locked. And those kind of mechanisms are used when you want some type of a constant force resisting the load. So I'll give you an example. If you think about it like this, say you have a, if you have a screw, a simple screw jack, if you have a screw jack that you want to use to raise your car. So you have a screw jack, and what you want to do is you want to raise your vehicle up. Okay. So what you want to do is somehow you want to rotate the screw, raise the vehicle up, remove this lever, and you still want the vehicle to be in its place. You don't want that vehicle to come down. So otherwise it would be bad. You won't be able to work underneath your vehicle. So this is self-locking. It means if you want the vehicle to go down, then you have to manually rotate the screw so that the jack can be raised up or down, and then the vehicle can go up or vehicle can come down. So this is the self-locking. There is another application, something like this. You want to use this screw for maybe sort of a punch operation or an operation where you want it to be holding. So you want to actually punch a hole. So in that case, you want this screw to be running so that the screw will come down and punch the hole. So this would be non-self-locking. So for self-locking, helix angle has to be greater or less than friction angle, and for non-self-locking, the helix angle has to be greater than friction angle. Now here is something that I want you to think about. If you have a self-locking screw, but if you increase the lubricant or if you increase the lubrication, then the coefficient of friction goes down. When the coefficient of friction goes down, the friction angle goes down. So sometimes if you have a self-locking screw, but if you add too much of lubrication, then that self-locking property is lost, as coefficient of friction mu dictates the value of phi. So tan inverse of mu. And mu depends upon lubrication. So you want to be very, very careful if you have a self-locking screw. Yeah.
So if we just see the two screws, can we tell this is non-self-locking and this self-locking?
Yeah, it's very easy. So for an example, if you have a screw, so if you have a screw something like this, what you do is you roll the screw up. So basically turn the screw and kind of raise this platform and let it go. If it's non-self-locking, it will rotate on its own and to the point that this thing will touch the base. So if it's non-self-locking, then it will actually run down and it will actually close. It will close on its own. So it will become like this. And if it's self-locking, you basically raise it up, it will stay where it is. So that is how you will actually judge whether the screw is self-locking or non-self-locking. Any other questions? So in screws, there is a concept which is known as lead. Lead is advancement of nut in one revolution of screw. So lead is advancement of nut in one revolution of screw. The second concept is, how do you find out the helix angle? Helix angle is lead divided by pi times diameter of the screw. So this is alpha. Alpha is equal to tan inverse of lead divided by pi times diameter of the screw. And this D is usually considered the mean diameter. Now, another thing that I want to talk about is the concept of pitch. So if you look at the screw, so pitch is the distance between successive turns. So for an example, if you look at the screw, this distance is the pitch. Now, there could be single start screw, there could be multi-start screw. In the case of single start screw, in one revolution of screw, the nut will advance by one pitch. If it's a multi-start screw, then in one revolution of screw, the nut would advance by the number of starts. So lead is equal to number of starts multiplied by the pitch. So if it's a single start screw, that means one start, the lead is equal to pitch. If it's a multi-start screw, then if you have two starts, then the lead is equal to 2 times the pitch. And with this information, we should be able to actually find out the design procedures for the screw and the screw jack. But there is one concept which I want to talk about. There are different ways a screw jack can be used. You can have a simple screw jack, the way I have shown over here. So I'm going to call this simple. Or you can have a toggle jack. So in the case of toggle jack, think about it like a turnbuckle. A nut here, a nut here, and you have the screw. Sorry about that. You have screw. Yeah, this is called as the toggle jack or the scissor jack. So I'll show you in just a second how it looks like. This is the type of jack that you will see in your cars. So what you have is clockwise threads on one side, you have counterclockwise threads on the other side. So if you rotate this screw in one direction, this platform will be raised. If you rotate this screw in the other direction, this platform will be lowered. So this is called as the scissor jack or the toggle jack. And this is the type of jack you will see in your automotive applications. And the reason for that is this can become super complex. I mean, super compact, even though the mechanism looks a little bit complex. So what you have is you have the nut, which clockwise and counterclockwise threads on the either side. You have a screw, and the screw will also have the same types of threads. And then here there is no threads. And then typically there will be some type of attachment point where you attach the lever and rotate. So there is one nut here. There is another nut here. There are going to be hinges. And there is going to be the base. And this is how the toggle jack is designed. Now the issue with toggle jack is if you look at the force that comes on the toggle jack, not entire force comes on the nut. So it totally depends upon the angle at which this nut is oriented. So just to give you an idea, if this angle is alpha, then if this is F cosine of alpha is equal to P. And F sine of alpha is going to be the force resisted by the nut. So this is P, nut. And if you look at the way the design is, this P gets divided on both sides. What you have is this load, the load P, gets shared by nut 1 and nut 2. So this, if you were to look at the force on each nut is going to be P divided by 2. So once you draw the free body diagram, with this free body diagram, you should be able to find out the value of force in each nut. So I will write this equation down. So first, I'm going to split this into P by 2, because the total load is P. This load gets shared by nut on the left and nut on the right. So I'm going to have this F. And please understand, for the toggle jack or the scissor jack to work properly, these angles should be the same. And I need to be very careful. I'm going to call this alpha 1, because this is not the helix angle. So these angles need to be the same, and both of them should change by the same amount. You cannot have two different angles, otherwise that assembly would lock. And then you are going to have F cosine of alpha, that is here, and you're going to have F sine alpha, which would be here. So first, let's find out the value of F. F is going to be P by 2 divided by cosine alpha, and the force in the nut is going to be P by 2 multiplied by sine of alpha 1 divided by cosine of alpha 1. So this is going to be P by 2 tan of alpha 1. Now, a word of caution. If you look at the textbook, the equation may look slightly different, because please note, I'm measuring my angle alpha from this vertical line. If you were to measure the alpha from the horizontal line, this would become cotangent, not tangent. It will become cotangent. So again, once you find the forces, the design statement would become something like this: design a power screw or a screw jack for load is equal to XYZ kilonewtons, and then they will give you the value of sigma T. So sigma T will be given to you, sigma C will be given to you, and value of tau will be given to you. They will also give you the value of friction angle, or they can give you the value of mu. So if they give you the value of mu, you can find out the friction angle by using the equation phi is equal to tan inverse of mu. Yeah.
So I did the homework. I don't remember. Is it the homework D or it was about the screw jack, and we don't have the tau, which is the shear stress.
So shear stress, depending upon what you use, typically the shear stress tau is 0.5 times sigma t.
Okay.
If that is not given to you, then you can assume that shear stress is equal to 0.5 times sigma t. So let's find out what are the stresses that come onto this assembly. So what are the stresses? So first and foremost, please understand, we need to find out the torque that is needed to raise the load. So if you look at the nut and screw assembly, if you look at the nut and screw assembly, you need to apply some torque so that this rod can be raised. And that torque T is given as W multiplied by the mean diameter of the screw divided by 2, which gives you the radius, tan phi plus alpha. So this is the mean radius, and W is the value of the load, and alpha is the helix angle, and phi is the friction angle. The next thing, if you want to find out what are the types of stresses that come on this assembly, I want you to think about for a minute that this screw is in motion. So when the screw is in motion, so the screw is either going up or going down, you have simultaneously the load acting on the screw as well as the torque acting on the screw. So please understand, when the screw or the screw jack is in operation, you are gonna have the load and the torque simultaneously acting on the screw. So what it means is you are gonna have normal stresses, say W divided by pi by 4 diameter of the screw, and the shear stresses, which is T divided by J multiplied by R. And these two stresses, when they act together, is going to give rise to principal stresses, sigma P, and maximum shear stress, tau max. Now, this is slightly different than the way we designed the turnbuckle. In turnbuckle, since there was no tau or there was no torque, we just designed the turnbuckle based on the normal stresses and shear stresses. But in the case of power screws, what you have is you have the normal stresses and shear stresses, both of them simultaneously acting, that gives rise to principal stress and maximum shear stress. So that is something that you should keep in mind, is if you want to design a power screw, then you will have to design it based on the principal stress and maximum shear stress criteria. So what I want to do is, I just want to take a simple problem, and then we will actually work on the complete design. So I just want to take a simple problem that kind of gives you some equations, how to use these equations, and then we will go through a problem where we will design the entire screw jack. So a screw jack is used to lift 30 kilonewtons. Coefficient of friction is 0.15. Pitch is equal to 3 millimeters. The mean diameter is 30 millimeters. Find maximum stress. So this is not actually a design problem, but this is a simple mechanics of material calculation problem, wherein the screw jack dimensions are given to us, coefficient of friction is given to us, the pitch and the mean diameter is given to us, and we have to find out the maximum stress. So I'm going to assume a single start screw. So I can find out the value of alpha. The pitch is equal to 3 millimeters. And this is pi times (30 millimeters). So tan inverse of 3 pi times 30, that gives me the value of alpha. Next, I can find out the value of phi, which is tan inverse of mu, which is 0.15, and that gives me the value of phi. So torque is equal to P multiplied by dm by 2 tan phi plus alpha. P is 30 kilonewtons. 30 divided by 2 multiplied by tan of P. Let me see how much is the value. Alpha is 1.8. I got alpha is 1.82 degrees, and phi I got 8.5. So 1.8 plus 8.5, that gives me the value of torque, which is 82 Newton meter. Now the load is given to us, so I can find out the stress, which is load divided by area, which is 30 kilonewton, 30 10 to the power 3, pi by 4, 30 square, that gives me 42.4 Newton per millimeter square. Tau value is given as T divided by J multiplied by R. T is 82 10 to the power 3. J is pi d raised to 4 by 32 multiplied by 30 divided by 2. That gives me 15.5 Newton per millimeter square. And since I have the normal stress, I have the shear stress, I need to find out the principal stress. Sigma P is equal to 1/2 sigma n plus square root of sigma n square plus 4 times tau square. So 1/2 42.4 plus square root of 42.4 square plus 4 times 15.5 square. That gives me 47.5 Newton per millimeter square. So as you can see in this problem, first we have to find out the torque that is needed to raise the load. We have from the torque, we'll find out the shear stress that is in the screw. Then we have to find out the normal stress. This is normal stress. This is the shear stress. Since normal stress and shear stress, both these stresses are acting simultaneously, we have to find out the principal stress. And that is how the screw jack would be designed. Now, I want to solve one more problem, a simple problem, before we actually start working out a design problem. Any questions in this problem? Everyone good so far with the calculations? Online students, any question? So next part is another problem. Let me just quickly work out. So a 2-start screw with 80 millimeter OD and 14 millimeter pitch supports 1.5 load, find torque needed to raise the load if nu is equal to 0.15. Now, one thing I just want to tell you that if you look at the screw, screw has outside diameter and it has the inside diameter. the mean diameter is DO plus DI divided by 2. The pitch is this distance. And typically, inside diameter is equal to outside diameter minus pitch. This is an approximate relation. So inside diameter is equal to outside diameter minus pitch. So in this particular problem, the outside diameter is given to us as 80 millimeters. Pitch is given to us as 14 millimeters. So the inside diameter is 66 millimeters. So the mean diameter is 80 plus 66 divided by 2, which is 73 millimeters. Helix angle alpha is equal to tan inverse of lead divided by pi times mean diameter. And the lead is number of starts. Please note the number of starts here is 2 multiplied by the pitch 14 divided by pi times 73. So alpha is 70. Just quickly work out this calculation and let me know if my answer matches with your answer. The coefficient of friction is 0.15. So phi is equal to tan inverse and you get 8.5 degrees. So the torque is W dm by 2 W is 1.5 kilonewton. Dm is 73 divided by 1000 times 2 multiplied by tan of 7 plus 8.5. And this becomes 0.03 kilonewton. So we worked out two problems, simple problems. Now what we will do is we will actually work out the entire screw jack. Any questions before we begin? Everyone understood the key steps? You had to find out the torque, we had to find out the principal stress, and then we have to use these equations to design a screw jack. So the design problem goes like this. Design a screw jack. To lift 80 kilonewtons through 400 millimeters. Sigma T is equal to 200 megapascals. Something I want, side note. Megapascals is 10 to the power 6, that's for mega. Pascals is Newton per meter square, which is same as Newton per millimeter square. So this is other way of saying this is 200 Newton per millimeter square. The nut material is Prosper bronze. And for Prosper bronze, sigma T is 100 Newton per millimeter square. Tau is 18 Newton per millimeter square. And here there is one more additional information that is given to us. The bearing pressure cannot exceed 18 Newton per millimeter square. So if you look at the whole screw jack assembly, you're going to observe something like this. There will be the screw. Then there will be this nut. This nut will be fitted in a housing. And then there will be a platform. On this platform, there will be a cup. And usually there will be a handle. So if you look at this assembly, housing, screw, nut, cup, and when we are expected to design a screw jack, you can go all the way up to design of nut, design of screw, design of cup, design of handle, design of base. Some of these dimensions, they come from the engineering analysis, like the equations that we used. Some of these equations, they come from the geometry. So for example, once you design the nut, once you design the screw, then you want to design the housing so that the nut can be attached. Then what you want to do is you want to have the handle of sufficient length so that you can rotate the screw, and then the cup can be raised up or down. And then you need to provide some type of tolerances so that the nut can be secured in the housing. Sometimes you'll notice that there is a set screw here. So there is usually a screw here, a screw or set screw that will hold the nut to the housing. So we will step by step proceed with the design. starting with the screw design, nut design, and then going to the housing, handle, cup, and so on. But one important observation here, that if you look at the handle, you have a choice. You can have the handle that can be rotated by two hands, which means you can have a handle that extends on both sides, or you can have a wheel that you can rotate. You can have a motor that is attached to the nut, I'm sorry, attached to the screw that can raise the screw up and down. So depending upon the load that needs to be raised, depending upon how fast or slow the load needs to be raised, then you can have a different type of assembly. You can actually have electric motor, or you can just have a long handle, or you can have a wheel that you can rotate. And depending upon the load, the friction, all these different configurations are possible. But one observation here is, imagine that there is this big load W. If there is this big load W, recognize at the interface of this cup and the platform, at the interface of this cup and this platform, there is going to be friction. And that friction is going to cause some resistance to the handle motion. But here is what we want to do. We want to rotate the handle, but there is a load which is acting on the platform and the cup. So there will be some additional frictional torque that you have to overcome so that this entire assembly can be raised up or lowered down. So sometimes you can give a conservative estimate and find out the amount of torque that is needed to raise the load, plus some torque that you need to supply to overcome the friction at the interface. So we'll look at those cases, but let's start with the first step, which is the screw design. So step one, screw design. In screw design, we are going to look at the compressive failure of the screw, compressive or crushing failure of screw, sigma C. Did they give us sigma C is not given, so we have to go to the design data book. And factor of safety, assuming 4, sigma C is equal to the yield stress in compression, 320 divided by factor of safety, and that gives me 80 Newton per millimeter square. So the load is 80 10 to power 3 and this gives me 80. So from here is 36 millimeter. So quickly check if this answer is correct. Now we are not going to cut the screws by ourselves. So we are not going to take a shaft and put it on the lathe and cut the screw. Screw is a catalog item. So you would go to Amazon, you would go to Vishay, you would go to, you can go to McMaster Car, you can go to Granger. and pick up the screw that's within this dimensions. So if you look at the machinery's handbook or design data book, so referring to design data, you would notice the preferred size for screw is 38 by 8 millimeter. This is the preferred size. So with this, I should be able to find out DI is equal to 38 millimeters, DO is equal to 46 millimeters, and pitch is equal to 8 millimeters. These dimensions come from the design data book. So you can actually Google design data preferred dimension for screws, or what you can do is you can go to MacMaster Car and it will show you the list of dimensions that are available for a particular type of screw. The next part is we need to find out the mean diameter and that gives me 42 millimeter. Now this is an open-ended design problem. The coefficient of friction is not given to us, but they have given us the material, Prosper bronze and steel. So what we will do is we'll find out the coefficient of friction for Prosper bronze and steel, and that is 0.15. This information also comes from design data. And if you don't have access to design data book, the important tables that are needed for design are given in the textbook. So that's why when we try to discuss the gear design, I want you to have access to the textbook so that we can refer to the appropriate design tables. So with this, I can find out the value of phi is tan inverse 0.15, 8.5 degrees. And then I'm going to assume a single start screw alpha pi em. Now with this, we can find out the torque that is needed to raise the load. So torque so P is 80 With that, I can find out the value of tau. $24.5 and sigma and with this we can find out the principal stresses. $66.7 is safe. So now we know that our nut design, the screw design is safe. Next step, step 2 is nut design. So sigma C is equal to P divided by pi by 4 d outside square minus d inside square multiplied by n, where that n will give you the number of threads. So sigma C, I'm going to assume this is for phosphor bronze because nut so sigma C is equal to 150 for phosphor bronze divided by a factor of 53. I'm going to assume 50 Newton per millimeter square because that's a softer material than steel. So 50, 80, I think 46 minus 46, 38 square multiplied by n. So n, I got answer 2.4. I'm assuming it to be 3. Now a word of caution. If you have a nut and if you have a screw, you need minimum 3 number of complete teeth or complete turns to be in engagement for a proper engagement. So whenever you have a screw and a nut assembly, you need at least 3 threads in complete engagement. Please understand, when the nut is designed or the screw is designed, initial threads are not complete. They are partial threads. So if you have a partial contact between the nut and the screw, that joint will not be safe. So at minimum, you need to have 3 threads in complete contact. But then you have to allow some threads for alignment. So for an example, when you screw into a nut, the initial threads do not provide the strength. they actually align the screw and the nut. And after that alignment is done, then the next set of screws and next set of threads, they get into the alignment, and that they provide the strength to the joint. So you have to always compensate for some clearances, some partial threads, and some alignment threads. So what that means is, even though from this design, it is saying that you just need 3 threads in contact, but from alignment point of view, from clearance point of view, you need to add additional threads to this assembly. So for safety, I'm going to say 3 plus 2 plus 1 for entry, 1 for exit. So this is N. So this is alignment. This is for entry, and this for exit. So total number of threads on the nut will be 7. And that is just to account for minimum number of threads from safety point of view. Now I want you to look at the nut design. So if you look at the nut, the nut is something like this. So as you can see, that there is a possibility that the threads can shear over here. The threads can shear over here. So what you need to do is you need to check for shearing. So tau is equal to P pi times D times T. This would be D outside. Now what is T? T is this total length. This T is going to be the number of threads multiplied by the pitch. And then you are going to have basically half of the threads in contact. So this will be T divided by 2. So 80 into the power 3. Okay, because if you look at the whole thread, this is the screw. So as you can see, from here to here, this is one pitch. If you look at this distance, this thickness, this is 8 divided by 2. I'll try to draw the pitch is from here to here. Right? But if you look at the thickness that is resisting the shear, it's half of the pitch. That's why. You see, you understood? About 20 Newton per millimeter square. Any questions? The next part, step 3, is handle design. And handle should be designed so that sufficient amount of torque can be applied. So total torque is equal to torque needed to raise the load plus friction torque. And this can be approximated to 1.2 times torque needed to raise the load. And that is 1.2 times 357. Now, depending upon whether you're applying the force by hand, whether you're applying the force by two hands, there are different values of forces. For example, if you want to apply some torque intermittently, you can go up to 500 Newton. If you want to apply the torque continuously, the torque applied by one hand can go up to 300 Newtons. Yeah.
Will the length of the hand affect the torque?
Yeah. So no, the length of the handle will be dependent on the amount of force a person is able to apply. So what it means is, for an example, you have this cup. Okay. This cup is mounted on this platform. And then here is the nut. And here is the screw. And now you have this handle that goes from here to here. So if you look at the torque, torque is force times the radius. Now, whether one person is applying the torque or two people are applying the torque, or whether you have a motor that is applying the torque, that will dictate what type of design we need to use. Now, what I'm going to do is I'll give you an example. Let's assume that a single person is applying the torque. So for that, you will actually go to the design data book and see how much force a person can apply, and say that force is typically 300 Newton. So average force by hand is 300 Newtons. So once you find out total torque divided by average force, that will give you the length of the handle. Now you will realize if you apply 300 Newton, if you look at the total torque, the length of the handle becomes 4 millimeters. So that's a long, very, very long handle. So clearly you cannot raise this load just by applying torque with one hand. So what you want to do is you want to come up with a slightly different design. And one potential design is, if you think about from the top view, you can have something like this, where there is one person applying torque here, another person applying torque here, one person applying torque here, and one person applying torque here. So basically, or what you can do is you can have a wheel where not just one, but multiple folks can raise or lower the load. So depending upon what you want to do, that is how this assembly is designed. The last part is step 4. You have to check for buckling. Now, what is buckling? Buckling is something like this. Think about if it's a long column, and if you apply a lot of load, rather than the column crushing, the column could actually just snap. So basically it would buckle. So if you apply a lot of load, rather than the column crushing, the column crumbles, and that is buckling. And to find buckling load, you can look at the textbook. The equation is W critical AC sigma C 1 plus sigma Y, actually 1 minus sigma Y 4 C pi square E L by K square. L by K square is called as the slenderness ratio. Total length is 400 plus 56 plus 40, which is about 500 millimeters. Sigma C is equal to 320 Newton per millimeter square. And you can substitute these values in this equation, and you will see the critical load is 443 kilonewton, which is much, much greater than 80 kilonewton. So the design is safe. And that is how you would design a power screw. And there are some additional dimensions, like the dimensions of the housing, dimension of the cup. Those come from the standard empirical dimensions. So those come from the proportions. Once you have the nut dimensions, once you have the screw dimension, you design the housing so that the nut and the screw can be accommodated. So if you look at the textbook, those non-critical dimensions are given to you. Let's take a break for 15 minutes, and then we will come back and we will start the next topic, which is the gear design. Okay, welcome to the last part of today's lesson. This will give you a little bit of introduction to the power transmissions and gears. So a simple concept. So it's like gears. Gears originate from friction wheels. So what do I mean by friction wheels? So we have one big wheel, and then there is another small wheel, Now, depending upon the ratio of their diameters, so I'm going to call this gear. And I'm going to call this small wheel pinion wheel. And this will be dp. Assuming dg divided by dp is equal to 4, which means diameter of the large wheel divided by the diameter of the small wheel is 4. One revolution of large wheel will cause 4 revolutions of small or pinion wheel. So this is called as gear ratio or reduction ratio. So what is the phenomenon that is causing this rotation? So I want you to understand the word is important here, which is friction wheel. So this power transmission or the torque transmission is happening because of friction. So if you look at the point of contact, this is called as the point of contact. At the point of contact, you have the normal reactions that are shown over here. So you have the normal reactions N, you have another normal reaction N over here, and the frictional force that is generated because of the normal reaction is F is equal to mu times N. And that frictional force F is causing this power to be transmitted. So I will try to explain this once again. So this is the line of centers, which means this is O of G, this is O of P. So this is O of G, this is O of P. And this is where you have the point of contact, which is P, O, C. At point of contact, you have these normal reactions N and N. And since these two wheels are in contact with each other and there is some friction, which is mu, what happens is you have the normal reaction N, frictional force because of the normal reaction is going to be mu times N, and this mu times N multiplied by their respective radii, which is Rg and this Rp, is going to cause torques. So torque on the gear is equal to mu N times the radius of the gear. Torque on the pinion is mu N times radius of the pinion. And please understand, the radius of gear is more than the radius of pinion. So radius of gear is more than the radius of pinion. What that means is torque on the gear is greater than torque on the pinion. Are you with me so far? Now, please understand, power can neither be created nor be destroyed, because power is nothing but energy divided by time. So if I were to write this equation, torque of the gear multiplied by the angular speed of the gear, torque of the gear multiplied by the angular speed of the gear, that gives me power of the gear. Power of the pinion is torque of the pinion multiplied by angular speed of the pinion. So what I can say is, since power can neither be created nor be destroyed, energy conservation assuming all other losses are zero, power P of G is equal to P of P. That gives me torque of the wheel and torque of the gear speed of the gear is equal to torque of the pinion, speed of the pinion. That gives me an important equation, T of G divided by T of P is equal to omega of P divided by omega of G. Now what I'm going to do is, I'm going to use this equation 1 and substitute that in equation 2. When I take equation 1 and substitute that in equation 2, please understand, I get R of G divided by R of P is equal to omega of P divided by omega of G. So essentially, the ratio of the radii, for example, if R of G divided by R of P is 4, which is same as diameter of the gear divided by diameter of the pinion is 4, which means one revolution of gear is going to give me 4 revolutions of pinion. So think about it like this. So this is 4, is 1. So omega P, and if I say 1 as omega of G, which means one revolution of gear is going to give me 4 revolutions of pinion. Now, one important thing that I want you to observe, that friction wheels are dependent on clearly the friction. Now, I want you to think about something like this. For some reason, I add a lot of lubricant or lubrication oil in between the gear and the pinion for the friction wheel. So I increase the amount of lubrication. What would happen? Coefficient of friction would go down, which means those two wheels would start slipping. And which means friction wheels will not work if the friction value is low or if the friction goes to 0. And what happens is you get slip. So these two wheels will slip, but there won't be any power transmission. So that's why what we want to do is we want to cut teeth. But here is the basic issue. For continuous and smooth power transmission, this is called as the law of gearing. And remember this all the time. So for smooth and continuous power transmission, point of contact is also called as POC, must be on line of centers. line joining the centers. So LOC. Now what that means is if you have a big gear, if you have a big gear and that is meshing the small pinion, then you want to cut the teeth in such a way that at the interface, the point of contact should be on line of centers. So what you have is you have teeth on the pinion, you have the teeth on the gear. They should mesh in such a way that when the power is transmitted, the point of contact is on the line of center. What happens if the point of contact is not on the line of center? In that case, the power transmission is not going to be smooth. There will be a lot of vibrations. So this is also called as law of gearing. Now I want you to think about it, the shape of the gears. So I have said 2 wheels, and what I'm going to do is I'm going to cut rectangular teeth. If I cut rectangular teeth, do you think they will be able to rotate freely? If I have a rectangular teeth on the gear and the rectangular teeth on the pinion, do you think that they would rotate or they would just get locked? They would get locked. Why? Because this rectangular shape does not have the kinematic conditions that are satisfied for the smooth engagement and disengagement. So let's imagine for a second that we have these rectangular teeth. What's going to happen if we let those rectangular teeth mesh? You realize that one tooth would eat into the other tooth. So basically they would scratch each other and the material would get removed, and you would realize at the end you are going to have a shape which is something like this. Do you agree with me?
Yes.
Now, why is this shape? Because this particular shape would ensure that those 2 teeth can engage and disengage without locking up. In other words, if you look at the way the whole geometry works, if you look at the kinematics, how the kinematics works, this can be visualized as if that you have a circle, and on this circle, what you have is you have a line, and this line is rolling on this circle. So this shape that is traced by the point on the line is similar to the shape that you need on the tooth for smooth power transmission. And this profile, it has a particular name. There are 2 ways this can be done. You can have a line that is tracing the profile, or you can have a circle that is tracing the profile. So this profile, when you have a line tracing the profile on the circle, is called as involute profile. If you have the circle tracing the profile, it is called as the cycloidal profile. So there are 2 types of gears. You have involute gears and you have cycloidal gears. Involute gears are cheaper to manufacture, they work fine, but they are noisy. Cycloidal gears, they are expensive, but they are stronger and they are quieter. If you look at the way the force gets transmitted from drive gear to a driven gear, unlike the friction wheel where the force is perpendicular, the force would be at an angle. And this angle is called as the pressure angle. And why we have a pressure angle? Because please understand, they are no longer wheels. You are cutting the teeth, and as the line of action of force is not perpendicular to the interface, it is at certain angle, and that angle with respect to vertical is called as the pressure angle. There are two types, two values that are commonly used for pressure angle. One is 14.5 degree pressure angle and 20 degrees pressure angle. Pressure angle is a design parameter. There are different types of gears. You can have something like a spur gear. You can have a rack and pinion. So spur gears, I have shown something like this. In rack and pinion, it is used in the steering wheels. What you have is you have a pinion, and then you have a horizontal gear. So a gear with infinite radius. So you have the pinion and you have the rack. You can have a helical gear. You can have a worm gear, worm wheel. You can have a bevel gear. And depending upon the applications, you can have what you can choose appropriate type of gears. Yeah.
If you have a manual car, which kind of gear do you want to use?
If you have a manual car, in the transmission, you will have lots of different types of gears. You can have the spur gear, you can have a planetary gear, you can have internal, external gears. So let me show you. External gears means gears that are like this. You can also have internal gears, which are gears like this. This is external. This is internal. You can have sort of a planetary gear train wherein you have the external gear, you have an internal gear, and then the internal gear rotates around the external gear. So you can have just a simple gear train wherein you have something like one gear meshing with other gear, meshing with another gear, and meshing with another gear. So you can have a simple gear train, and this could be a gearbox in manual gear transmission, or you could have complex planetary gearbox wherein you have the planetary gears. You can have the combinations of spur gear, helical gears, depending upon the amount of torque that needs to be transmitted, the reduction ratios that you want. And if you look at the differential, rear differential, you usually have a bevel gear, wherein you have a gear like this. You have the gear that comes from the prop shaft, and you have the gear like this that goes to the wheel. So this is the prop shaft. And if you see, there is this pumpkin in the rear differential. So you have a rear differential wherein you have these line of actions or the shafts. If you look at the center lines of the shafts, they are at 90 degrees.
But what about if we shift like from 1 to 2?
So you use a clutch. So
Yeah,
basically what you do is you,
yeah,
you
so
clutch.
How the gear shift?
Okay. So we will talk about the gear train, but let me show you what it means. So in the first gear, what you want is you want low speed So, and you want low speed and high torque. So this is the first gear. And think about that. I'm just going to show you a simple, here is the engine. This is connected to engine. Where the engine is. And just for the sake of discussion, let me show you. And here, this is the second gear. So what's going to happen is, initially it is in the first gear, there would be a clutch. You would declutch it, and then there will be a arm that would push this gear onto this spline shaft. So what would happen is that the first gear, there would be a sleeve here. This first gear would get out of engagement, and the second gear, this is the second gear, would come into engagement, and that would change the speed of the wheel. So as you can see that this first gear, the whole thing is a spline shaft. So what you have is, you have a spline shaft, splines on this shaft, and this gear can slide back and forth. This gear can basically slide back and forth. And then you would have a shifter lever, or you can have some type of a hydraulic, or usually maybe differential pressure diaphragms that would actually shift the whole thing left or right. Okay, I'm going to stop here, but we'll continue the discussion again in next class.